Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 9.4, Complex Solution of Auxiliary Equations. So what actually happens if the auxiliary equation gives you a complex solution? Well, that would be an oscillatory solution, which means that sine and cosines would be involved. Later on, we will cover a certain aspect of this complex solution and head over into the realm of something called the simple harmonic motion oscillation, which essentially is the same as this topic, but we need to elaborate a bit more on that part. So for the purpose of this video, I'm gonna ignore the particular integral and make this equation homogeneous. So with that, we can save ourselves half the time. But in the exam, you will be asked to have to answer a certain particular integral, and it's for demonstration purpose that I skip that step, because it's gonna be the same as last video anyway, or maybe the next video. So let's have a look. Auxiliary equation, lambda squared plus lambda plus 5 goes to 0. Everything is positive, so we know that it's highly unlikely that it's gonna be real. So let's do the quadratic formula such that lambda is equal to minus b plus or minus the square root of b squared, which is 1, minus 4 lots of AC, which is 20, all over 2a, that is. With that, we have two lambdas, one with a plus root, one with a negative 1 root. However, they are all roots minus 19, which means that we have minus 1 plus or minus root 19 of I on 2. So I've got these two lambdas. So after we've done this solution, we use the normal as we would format. X equals to AE to the minus 1 plus root 19I all on 2 plus B e to the minus 1 plus root 19I on 2. Remember, you have the t following the lambda. So that works as we do normally. However, this part, this plus, this addition can be split by index law, such that you're left with a e to the minus a half e to the root 19 on 2 I t add b e to the minus a half t e to the root 19 on 2 negative t, because for the b it's actually negative, which is my bad, plus and minus, remember. So with this, we can kind of factorize the e to the minus half t out, and remember that because we have an I on the exponential, we can use the trigonometric function, and it's essentially it turns into the complex let's see, arcant exponential form, and turns out that we can write this whole thing after a lot of algebra, which I'm not going to demonstrate, into e to the minus a half a cos root 19 onto t, whoops, plus b sine root 19 onto t. So bear in mind that the cosine and the sine are both real, or because of the negative sign that determines the plus and the real and unreal parts. And turns out that this works as a general solution from this whole mess. And you are only required to know in a general form that the solution is e to the real part multiplied by a cos the imaginary part t plus b sine the imaginary part of t. So this is the general format of the oscillatory solutions. A and b can be any real value, so just split your solution of the auxiliary equation into the real and complex, real and imaginary parts. Then you can find the general solution like this. So it's kind of straightforward. So for this complex auxiliary, make sure if you are doing the particular integral that involves trigonometric functions, which are oscillatory, then you need to do a trial function including both sine and cosine. So if it is if the right hand side of the equation is, say, cosine of 5t, then your trial function would be a sine of 5t plus b cos of 5t, because sine and cosines will switch around after differentiating, which means that if you don't include one of the other, if you exclude one or the other, then you would miss out half of your trial function and things will not cancel. So it's gonna be bad, to say the least. Also for this, make sure you remember the general solution, because you do not actually need to derive the general solution. You can just jump straight from the auxiliary solution right to the general solution format. So if you remember how to write the general solution in the terms of the real and imaginary parts, then you would save yourself a lot of time during your exam. Right, so we have come to the question section. I think I have missaid that the left part is so what I mean is that the left part of your solution is actually called the complementary function, not the general solution, which is very bad of me. The general solution is the complementary function plus the particular integral. That would be our general solution. So for the questions, find the general solution of the following, which includes the particular integral. I hope that help clear things up, because terminology is quite important in mathematics here, and I apologize for saying the wrong things. Anyway, as usual, I'll give you 5 seconds to carry out the calculations, and I'll show you the answer in 5, 4, 3, 2, 1. And the answer is shown right here. So for the first one, it's straightforward, really simple. The second one is a bit more interesting, with the particular integral being a trigonometric function, and you would have to do some, differentiation to a negative cos and negative sine. Then you have to cancel out things, and you ended up with plus a12 cos 2t. The second one is strikingly similar to the future topic, simple harmonic motion, except the fact that I had added a particular integral onto it. And I'm not gonna spoil that for you, and I'll talk to you about it in some coming videos. But for now, thank you very much for watching, and I will see you on my next one.